Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my pleasure to introduce Neil Koblitz. Neil and I have been colleagues and friends for almost 25 years now. I've learned over the years that when Neil has something to say, it's always worth listening to. So he will speak to us today on my last 24 years in crypto, a few good judgments, and many bad ones. Neil?
Thank you, Scott. Thank you for the opportunity to speak here. I won't be saying anything about the invention of ECC, so that's why I have 24 years in the title. Rather, my basic theme will be about how easy it is to make bad misjudgments in cryptography, and I'll illustrate that by an abbreviated history of my own bad mistakes over the last years. But the early part of my talk will be about how conventional wisdom perhaps can sometimes be wrong. And that's based on a paper that will hopefully appear in the finite future in the special ECC issue of the Journal of Number Theory. And this is a joint paper with Alfred Menezes and my wife, Ann Hibner Koblitz. In the meantime, you can easily find it on the IACR ePrint server by it's the only paper there with the word serpentine in its title. It's called ECC, the Serpentine Course of a Paradigm Shift. So the first part of my talk will be about a section of that paper concerned with the security implications of isogeny walks in the isogeny class of an elliptic curve. That's section 11 of the paper. But I also want to say that I strongly recommend that if you look at the paper that you read section 13, which contains discussion of such interesting topics as family life of gorillas, controversy over whether or not the ancient Native American tribes of Arizona were warlike, the implications of Alan Sokol's hermeneutics of quantum gravity, smart houses with robotic butlers, and other topics that are rarely treated in the pages of the Journal of Number Theory. Okay. So to start, the conventional wisdom in cryptography is that when possible, it's always a good idea to choose, from a security standpoint, to choose parameters as randomly as possible. And in particular, in both elliptic and hyperelliptic curve cryptography, the safest choice is to have defining equations with randomly generated coefficients. Now, continuing with the conventional wisdom, it might be all right, or probably all right, to use special curves for reasons of efficiency if you really want to. But someday that choice of curves with special properties might lead to an easier attack by an adversary. So there's some risk associated with that choice. That is the conventional wisdom. Now, in 1991, I proposed the use of non-supersingular curves defined over the field of two elements, of which there are two with these equations, these two equations, also called anomalous binary curves, because they seem to me to have some efficiency advantages over random curves. Well, the NSA liked these curves, and at Crypto 1997, Jerry Salinas gave a talk presenting a thorough and definitive treatment of how to optimize point multiplication on these curves. I believe it was the first talk given publicly at a crypto meeting by an NSA person. At present, these curves are one of three families of NIST recommended curves, each over 5 possible choices of finite field at different security levels. Now, some people have been mistrustful of this particular family of anomalous binary curves, in part because of the conventional wisdom that I gave above that argued for random parameter selection. There have been two other arguments besides the conventional wisdom that I want to mention. One of them, around the time that I presented the proposal for these curves, Klaus Schnorr very much objected, and in fact he objected to the use of any elliptic curves over binary fields because, as Vic Miller explained this morning, in the early 80s there was the L of 1/3 algorithm by Coppersmith that to solve the discrete log problem in the multiplicative group of a binary field. And until somewhat later, about a decade later, with Dan Gordon's algorithm, it wasn't known that there would also be L of 1/3 algorithms for the discrete log in multiplicative group of more general finite fields. So the initial impression during a period of about a decade was that the multiplicative group was far more vulnerable in characteristic 2. And so Schnorr thought that maybe that vulnerability would carry over to elliptic curves defined over binary field. But that argument basically fell through when L of 1/3 algorithms were developed for prime fields and other fields. There's also a second argument which was harder to refute. It took the form of a syllogism. It said the NSA wants us to use these curves. We don't trust the NSA, therefore we don't trust these curves. Now this is harder to refute, but you can use a type of organizational analysis, sort of in social science, to explain why it is that I don't accept, and many people don't accept this syllogism and are willing to use these curves. So let me present that. The NSA isn't a monolith. Just because NSA mathematicians recommend a family of curves, it doesn't necessarily follow that they're no good. Now, I think the best way to depict this organizational analysis is with the use of PowerPoint clip art. So here is my analysis that the people we love to hate wearing the black hats at NSA are not the same ones as the ones who are recommending these curves. The nice thing I should say about this organizational analysis is that it carries over. There's nothing special about the NSA here. This organizational analysis carries over to other organizations that are of relevance to cryptography, thanks to the miracles of PowerPoint, especially the duplicate slide feature. So here's the corporate world, a similar dichotomy, and the university world. By the way, my wife, who's a professor of women's studies, objected that I've used male images for all 6 of these people. But my answer to that is, in the first place, there aren't 6 images here. There's 1 image repeated 6 times. And in the second place, I just couldn't find in PowerPoint clip art any depictions of dweeby nerd heads who were female. So that's why I use these images. Pardon? OK, now to return to the issue here of random versus special parameter selection, Alfred Menezes and I found some reasons to question the conventional wisdom that the random choice is always the more secure one. We claim that there are various scenarios where someone might choose ECC with a special curve and end up better off from a security point of view, conceivably, than someone who chooses a random curve. And these scenarios are based on recent work on isogenies. And that's the subject of section 11 of the Serpentine paper. So suppose we have 2 curves defined over the field of Q elements. An isogeny is a non-constant rational map that takes the point of affinity to itself. Its degree in our setting, anyway, we'll be dealing with ordinary curves, is also the order of the kernel of the isogeny. There's a dual isogeny going the other way in such a case, and this gives us an equivalence class, the isogeny class of a given elliptic curve. And by a fundamental theorem of Tate that Gerhard Frey talked about this morning, that 2 curves are isogynous over the field FQ if and only if they have the same number of FQ points. Now, from a practical standpoint, the basic situation, at least in our setting, is that low-degree isogenies are easy to construct, but high-degree isogenies are usually not, or they're usually not in the setting that we're going to want to one has to be careful about saying that in some settings, high isogeny, degree isogenies can be constructed efficiently, but not in the setting we're going to be dealing with. Now, within the equivalence class of isogenies, it breaks down further according to the endomorphism ring. And here, by an endomorphism, we just mean an isogeny from the curve to itself that in general is defined over the algebraic closure of the field of definition, but we're going to be working only with the ordinary, the non-supersingular case, where the trace T that's given here is prime to Q. And in that case, the endomorphisms are all defined over the field of definition. So that will be the situation we'll be in. Now, the endomorphism ring, denoted N of E, contains a subring, and naturally contains the integers as a subring. And to determine it further, we look at the discriminant of the curve, capital delta here, which is the trace squared minus 4Q. Now, the field generated by the square root of the discriminant is the complex multiplication field. And if we write the discriminant as a square times a fundamental discriminant of the quadratic imaginary field, that C0 plays a big role. The square part of the discriminant plays a big role in classifying the endomorphism rings of all the elliptic curves that have the same number of elements. Well, in general, the endomorphism ring is an order of the ring of integers of the CM field, and its index in the full ring of integers, denoted C, is called the conductor of the endomorphism ring. And the basic fact about that is that it's a divisor of C0. And in fact, there's a one-to-one correspondence between the divisors of C0 and possible endomorphism rings. So the elliptic curves that are isogenious to a given elliptic curve can be partitioned according to their endomorphism ring. And the endomorphism classes are determined by the conductors that are in one-to-one correspondence with all possible divisors of C0. Okay, now, and the other thing to know is that the number of isomorphism classes of elliptic curves in a given endomorphism class is equal to the class number of the order, and that's essentially or very close to the conductor C times the class number of the CM field. So the number of endomorphisms, and this is a basic point that we use, is that the number of isomorphism classes in a given endomorphism class depends very much, is basically proportional to the conductor C. So if there's a large conductor C, well, here's, for example, at one extreme, if the discriminant is square free, then there's only one endomorphism class. That all of the curves have complex multiplication by the full ring. On the other hand, if C0 itself is a large prime, then there are two endomorphism classes within the isogeny class. One is a very small one consisting of the curves whose endomorphism ring is the full ring of integers. And the remaining curves, almost all of them, have endomorphism ring of conductor C0, which is prime in this case. Now, let L denote a prime. If there is a degree, a basic fact is that if there is a degree L isogeny between two curves, then either the two curves have the same endomorphism ring, or else the conductors differ by a factor of L. Now, when we talk about two conductor classes that have different conductors, by the conductor gap, we mean the largest prime that divides one conductor and not the other. And so the basic situation as far as computation goes is that if there is a large conductor gap, that is a large prime that divides one conductor and not the other, then one cannot go from a curve in one class to a curve in the other by a string of low degree isogenies. And to the best of my knowledge, there is no efficient way known to construct an isogeny that goes from one class to the other. Conversely, by a result of Zhao, Miller, and Venkatesan, within an endomorphism class or among classes with small conductor gaps, one can move efficiently, uniformly, using relatively easily constructed low-degree isogenies. Now, the security implications of these isogenies are that they allow one to transport the discrete log problem from one curve to another. So you can say that the discrete log problem is random self-reducible within a set of endomorphism classes with small conductor gaps. So you can efficiently move around and in some sense the security of your curve is determined by the lowest security of curves in that class. And so by the L conductor gap class of a curve, we mean that all of the endomorphism classes in its isogeny class that have a conductor gap less than L. So it's sort of like the relation between the conductor of E and the conductor of all the other curves in the L conductor gap class is a smooth number. So L is like a smoothness bound. There's no prime larger than L that differs between E and the elliptic curves in that class. So here's a hypothetical scenario. Suppose that an algorithm were found that solves the discrete log problem in time t1 in a proportion epsilon of all elliptic curves over fq, where epsilon is a very small but not a negligible proportion of all curves, where the property of being a weak curve is independent of the isogeny and endomorphism class. So it's basically the same proportion epsilon within any such class. And I'm also assuming here that once you go to an elliptic curve, you can quickly, efficiently identify whether or not it's a weak one. Then what this means is the discrete log can be found on any curve in an L conductor gap class in time roughly t1 plus t2 over epsilon, where t2 denotes the time needed to construct these isogenies. So we're moving around within a class where the isogenies are relatively easy to construct, and t2 is an estimate for the time it takes to construct such an isogeny. So basically t2 over epsilon is the amount of time it takes us to get to a weak curve, and then it takes us time t1 to solve the discrete log problem there. Now this assumes that the L conductor gap class, where L is this bound on the conductor gap, where we're able to construct isogenies in time t2. So t2 is the amount of time it takes us to construct isogenies that take us throughout this L conductor gap class, and we're assuming that the class contains at least 1 over epsilon curves if we're going to have any chance of finding a weak curve. So that's another assumption that's being made in this time estimate. Now, it's the possibility of random isogeny walks through a conductor gap class that might, under various sort of hypothetical circumstances, make a random curve less secure than a special curve. Now, it's crucial to note that for a random curve, basically we can move all the way, we can move all around. That all isogenous curves are in the same conductor gap class for a small l, the same L conductor gap class for quite small l, because for a random, an elliptic curve with random coefficients, the discriminant has negligible probability of being divisible by the square of a large prime. It's going to be almost square free. So here's a hypothetical scenario. And this scenario, there's several examples in the paper. The one that I want to talk about is over a prime degree extension of the field of 2 elements. Now let's suppose that some version of, say, Weil descent or some other approach, that may be one that's not currently known, someday leads to a faster than square root attack on a small but non-negligible proportion of curves defined over this particular prime degree extension of F2. Now I should say that this is not as far-fetched as it might seem, because there's been a lot of study of Weil descent in the context of composite degree extensions of F2. And there are certain cases, certain composite degree extensions of F2, where the Weil descent methods have been shown to work efficiently or relatively efficiently, give a faster than square root attack on the discrete log problem on a certain proportion epsilon that is small but not negligible. So this hypothetical assumption is very speculative for prime degree extensions of F2, but it is not speculative for certain composite degree extensions of F2. Okay, now as I mentioned, the NIST 2000 digital signature standard recommendations list 5 elliptic curves over prime fields, 5 random elliptic curves over binary fields, and 5 anomalous binary curves over those same 5 binary fields. So for each of 5 binary fields, they suggest 1 random curve and 1 anomalous binary curve. The highest security level is the degree 571 extension of F2, which is expected to provide more than enough security to protect 256-bit AES private key. So that's the highest level of security. So let's look at that case of the anomalous binary curve versus the random curve over the field of 2 to the 571. Now, the conventional wisdom would be that, if anything, the random curve, which they denote B571, would be its safer choice in the anomalous binary curve K571. However, let's suppose that a proportion epsilon of all curves over this particular field of degree 571 could be attacked by a new faster than square root algorithm. And again, we'll assume that the weak property is independent of isogeny and endomorphism class. Now, it turns out for the particular random curve that they generated and that NIST recommends, B571 has square-free discriminant. So isogeny walks can fan out over the entire isogeny class, which consists of about 2 to 285 curves. So there are plenty of curves there to range through randomly. And so after about 1 over epsilon isogenies, the discrete log problem on the NIST curve can be transported to a weak curve under these very hypothetical assumptions. Meanwhile, back in the land of special curves, the anomalous binary curve over the same field has discriminant of a radically different form, namely -7 times a perfect square. And it so happens, just by coincidence, I guess, that that number squared is divisible by a very large prime, a 263-bit prime. Now, the endomorphism ring of the special curve that you construct, the curve that's defined over the field of 2 elements, has conductor 1. In other words, it's easy to see, in fact, explicitly that it has endomorphisms by the full ring of integers of q of root -7. So if we want to range from that special curve to other curves, but we certainly are not, as a practical matter, to the best of our knowledge, or at least certainly to the best of my knowledge, we would just absolutely never be able to construct an isogeny that would bridge the gap of this 263-bit prime. So we wouldn't be able to go from our special curve to any of the curves whose conductor is divisible by that 263-bit prime. And so if we just move around within our 2 to the 262 conductor gap class, there are only about there are about 4 million curves there. So if epsilon is significantly less than 1 out of 4 million, the discrete log problem on K571 probably cannot be transported to a weak curve by means of isogenies. So under such a hypothetical assumption, K571 is actually likely to be the safer choice, contrary to the conventional wisdom. Okay, so what conclusions do we want to draw, do we draw in our paper about this? We do not say that that means we should prefer special curves over random ones. We don't just simply reverse the signs on the conventional wisdom and say just do the opposite. We certainly have not given convincing evidence of that. All we can really conclude is that we don't know. It's an open question. It's a judgment call. And I think that one of the basic things that we're learning as time goes on is that an awful lot of cryptography is that way. And despite the natural desire of cryptographic researchers to give an impression of certainty about what we do, in fact, cryptography is in many ways more an art than a science. Let me mention also, sort of parenthetically, without giving a whole lot of details, is that one can give a similar example over a prime field, a very elementary example, in fact, of an elliptic curve. Just choose a random prime b and a random even number a, such that a squared plus b squared is prime. And we're going to be using simplest possible elliptic curve here. Also, we'll want to assume that either p plus 1 minus 2a or p plus 1 plus 2a is twice a prime, so that because that's going to be mean that the number of points on this curve is going to be twice a prime. So in that case, the elliptic curve over the field of p elements, where p is constructed this way, you have to choose a to be in a suitable quartic residue class in FP, but it's easy to do. And then you find that y squared equals x cubed minus ax has twice n, 2n points where n is a prime. And it also that it's the only curve up to isomorphism in its conductor gap class where the conductor gap is basically b. That in that case, you actually have a case where the C0, in my earlier notation, the maximum possible conductor is equal to b. That's why we chose b to be prime. And so you have a situation where you have this one little curve that you write down the equation for. It's completely isolated in its isogeny class, that all the other, in the sense that all the other curves in the isogeny class have conductor b, and they are basically unreachable by this curve using isogenies, because we can't construct an isogeny in practice of degree b that will take it to another curve. So this would be another example that's very similar, where under certain hypothetical assumptions, this curve would be safer than a random curve over the same prime field. However, in this case, there is no family of special curves recommended by NIST over prime fields, so you're sort of stuck with the random ones whether you like it or not. Also, I want to remark that my PhD student, Wenhan Wang, misspells Wenhan Wang, W-A-N-G, has found that a very similar situation exists for genus 2 curves. That is, if you look at curves over a prime field whose Jacobians have a large endomorphism ring, like, say, the endomorphism ring of the ring of integers of fifth roots of unity, that they're often quite isolated in the sense that you can't travel widely from them to other curves using isogeny walks. So I think the same type of considerations will be relevant in hyperelliptic curve cryptography in genus 2. Okay, so now I want to, in the second half of my talk about, shift gears and talk a little bit about history of embarrassing misjudgments that I've made in the last 24 years, and then make some general comments after that. This will not be a complete history of that. The first major misjudgment I made was in the late 1980s. It seemed to me that any elliptic curve group would be secure as long as its order is prime or almost prime. And so when I gave talks or wrote about it, I wrote an introductory textbook in 1987. I thought, well, for pedagogical reasons, why not use the simplest possible curves? So I used the curves. This first one was discussed earlier today, y squared equals x cubed minus x, with 4 dividing p minus 1, dividing p plus 1, or y squared plus y equals x cubed. Both of those curves, provided that p has that divisibility property, has group order p plus 1. It's a very easy exercise for students to show this. So why not use this as an illustration of cryptography? And as far as I was concerned, that meant that ECC would be secure. So this is a nice example to give at every opportunity. It also turns out that not so much over the prime field as much as over field extensions of F2 and F3, these two equations, there are some nice efficiency advantages for computing point multiples. Basically that you get doubling of points for free over in characteristic 2 and tripling of points for free in characteristic 3. So they were sort of an attractive family of curves, I thought. And then, as is well known, in 1991, the Menezes-Okamoto-Vanstone result used the Bay pairing to give a reduction of the elliptic curve discrete log problem to the discrete log problem on the multiplicative group of an extension of the field of definition. And for supersingular curves, such as the two written above, the extension degree is very, very small. In fact, it's 2. So these were really weak curves, especially the ones that I'd written down with extension degree 2. And this came as a big surprise to me and made me feel very embarrassed that I'd use these curves so often for expository purposes. This basically kills supersingular curves for ECC, and was sort of traumatic for people like me who just found them so much fun to use in talks and so on. But I should say that the one thing that was even more surprising to me than the Menezes-Okamoto-Vanstone algorithm that killed ECC for supersingular curves was the fact that these same supersingular curves, or closely related ones, may return from the grave. They had a resurrection, and 10 years later they came roaring back when pairing-based cryptography took the research community by storm. So that also came as a big surprise to me. And of course, pairing-based cryptography is not used only with supersingular curves. They're also used with low embedding degree non-supersingular curves. But they are often used, and even in commercial settings, with supersingular curves. So this was quite interesting. OK, so the next embarrassing episode, actually, before I get to this next embarrassing episode, this one is not the next one. The next embarrassing episode, which I don't have on the slides, occurred in the late 80s when I proposed hyperelliptic curve cryptography, because if you had asked me at that time, I would have said that the higher the genus, the more secure the curve. That was the most likely thing. That was my instincts. I really have great instincts, don't I? So when I proposed hyperelliptic curve cryptography, that's what I thought was most likely. You know, high genus means more complicated curves. And so the algorithm by Adelman, Damaris, Huang took me completely by surprise. And then subsequent work by a large number of other people have brought us to the situation where the only version of hyperelliptic curve cryptography that seems to be fully competitive with elliptic curve cryptography is genus 2. So I couldn't have been more wrong about that. OK, so now, after that, the next embarrassing episode was in the early 1990s when my colleague Mike Fellows and I became captivated by the idea that despite the fiasco with knapsack-based crypto systems, you could, in fact, construct some good crypto systems using NP-hard combinatorial problems rather than just sort of number theory and algebraic problems. We even wrote a paper with the exuberant title, Combinatorial Crypto Systems Galore, which we published. Well, there was only one actual crypto system that we developed in any detail, and it had a rather sorry history. And I'll quote from my book, Random Curves, where I talk about this episode. What we constructed was a system based on the ideal membership problem that involved polynomials, and we challenged people to try to crack it. And the only thing that was really neat, and I'm really proud about this crypto system, is the name that we gave it. It was Mike Fellows' idea to call it Polycracker. So anyway, it was a very inefficient system, super inefficient. And before long, some papers were published that actually cracked the code. So that was another sort of mistaken episode. OK, so now let me return to ECC and get to more relevant types of mistakes related to ECC. OK, now during the first 15 years of ECC throughout the 90s, my feeling was that it didn't really matter what field you worked over. You had to avoid generic algorithms by working in groups of large prime order, and after the Menezes-Okamoto-Vanstone algorithm, you had to avoid supersingular curves, But other than that, you could use whatever field you most enjoy, and security would be unaffected by the choice of whatever field you worked in. But in the late 1990s, Professor Fry proposed Weil descent to attack the discrete log problem on curves over composite degree extension fields. And then a number of other people, Gaudry, Hess, Smart, Galbraith, Menezes, Teskey, and some others, found weak curves over certain binary fields. That's what I alluded to before, that certain composite degree extensions of F2 have weak curves in them. Now, fortunately, other people, most notably Scott Vanstone, had much better instincts than I had, and as a result of that, fortunately, all commercial implementations and all ECC standards used either prime fields or prime degree extension fields, and as far as we know, those fields, at least in the cryptographic range of interest, there's no security problems caused by Weil descent for any of the fields, curves over the fields using commercial implementations and standards. Okay. But I was really, on many occasions, quite bad at anticipating future developments. For example, in 1998, I published a book called Algebraic Aspects of Cryptography. And I wanted to include some things in it which were of great mathematical importance, but I thought were sort of not important, not really relevant to cryptography, but were so important to the history of the culture of the field that I should at least briefly say something about them. So in one such place, I discussed the Burchant, Swinnerton, and Dyer conjecture, and I essentially apologized to my readers for taking up their valuable time with something which, though of interest to mathematicians, has no relevance to cryptography. So this was in early 1998. 8 months later, I received an email from Joe Silverman outlining a striking new attack on the elliptic curve discrete log problem, which he called Zedny calculus. It was a variant of index calculus doing things in a somewhat backwards order. And he called it Zedny calculus because that was index spelled backwards. But what was really unexpected, other than just having a brand new algorithm to attack the ECDLP, was that Joe Silverman used the heuristics of the Burchant, Swinnerton, and Dyer conjecture, along with an analytic rank formula of Mestre, to increase the heuristic likelihood of a successful attack on the discrete log problem. So what made it at first seem so very difficult to analyze the likelihood of success of this attack was precisely that he was using the Burchant, Swinnerton, and Dyer conjecture, or the heuristics behind it anyway, to give reason for a greater likelihood of success. Well, there's a lot of initial worry about Zedny because it came at a time when there was a lot of worry that the RSA people would use Zedny as a weapon in their public relations battle against ECC, which was still going strong at that time. But I found that we could use the height function to show that Zedny wouldn't work. And I was so thrilled about this success in defending ECC that I gave a talk at ECC 2000. Gerhard Frey was very generous to me this morning about my Golden Shield talk. Well, I'm not saying it was a bad talk, but certainly the title of the talk is a source of embarrassment for me now. Miracles of the Height Function, a Golden Shield Protecting ECC. So I think that was in a way, well, it was overhyped. So now I should also say at about the same time a paper by Joe Silverman and Joe Suzuki made a detailed examination of index calculus and explained why it wouldn't work. Their paper essentially elaborated on the argument that Vic Miller made in his original 1985 ECC paper. Went into a little bit more detail. Also, at ECC 2007, 3 years ago, Silverman made a similar analysis for all 4 ways one could conceivably try index or Zedny with liftings to global fields, and concluding the same, that thanks to the miracles of the height function, none of them would be the least bit practical. So at this point, my feeling was that we had nothing to worry about from index calculus, whether spelled forward, backwards, sideways. That index calculus is not a problem at all. But alas, very recently, index calculus has reared its evil head in the world of elliptic curves. And for example, Gaudry and Diem found sub-exponential index calculus algorithms on composite degree extension fields if the Q and the M grow in a suitable way. And we'll be having a talk, as you know, later in the week by Menezes about improvements on this work by Gaudry and Diem. So index calculus is a live issue for the elliptic curve discrete logarithm problem, unfortunately, or embarrassingly. So I want to make some broader comments now. I think it's regrettable that so much cryptographic writing exudes a type of brash certainty about the work. And as I've said, I've been guilty of this. Certainly in my talk, in the title of my talk 10 years ago about the miracles of the height function, now, as I get older, I've realized that there are no miracles. And so I no longer believe in miracles, and I no longer believe in golden shields. But at the time, I was guilty of exuding a certain brash confidence about the work. And when you look at abstracts and introductions to papers, if you browse through the IACR ePrint server, they're often written not as if they're written by scientists, but as if they're written by marketing people, or maybe as part of a patent application. You might remember the slide of the black hats and the white hats about marketing people. But anyway, and you have, sometimes they're written with hype, with advertisement that has little connection to reality. And here, let me give an example, which by no means is unusual. Okay, so this is a paper from 3 years ago saying that their protocol permits savings on bandwidth and storage, improves computational efficiency and scalability. In contrast to the only prior scheme to provide this functionality, ours offers improved security, formal security definitions. We support the proposed scheme with security proofs. This was a paper by Baldyrieva, Gentry, O'Neill, Yum that proposed a way of what's called sequential aggregate signatures based on pairing for purposes such as security of network routing protocols and other applications, where several people in a sequence compose a single compact signature. But the reason why I mention this example, that the amusing thing is that about a year later, Huang, Li, and Jung showed that a crucial security proof in this paper was fallacious. They also broke the corresponding protocol. Now, there have been many cases like this of rather bold claims being made of protocols that were provably secure. And despite the questionable history of a lot of these claims, still one often reads the argument that these proofs of security can be offered to the public as a guarantee. So here's
all your example shows is that they did not have a proof. It's not that a proof of security would be bad, it's just that they didn't have it.
You're right, yeah.
Okay. Can you repeat? Just wanted to make that
Yes, thank you, Shaffer. Yes, okay, let me clarify that. Yeah, I have not given evidence that a proof of security would be bad. I've only said that in this case and in some other cases, proof of security turned out to be fallacious. Let me quote from the preface to a well-known book by Katz and Lindell. Cryptographic constructions can be proven secure with respect to a clearly stated definition of security and relative to a well-defined cryptographic assumption. This is the essence of modern cryptography and what has transformed cryptography from an art to a science. The importance of this idea cannot be overemphasized. Now, sometimes when people get dismayed because there is quite a history of fallacious proofs in the provable security literature, one of the possible responses is that advances in theorem-proving software will soon make it possible to prove the security of cryptographic protocols automatically without any longer any possibility whatsoever of flaws in the proof. And that will remove the element of human mistakes and failings. And I guess what some people might mean by making something into a science is precisely to do that. And will remove the human element from the process of establishing guarantees of security. I wrote a paper on this examining some of the theorem-proving work. And here's a reference for that if you're interested. Another issue that some people find bewildering is the rather ornate nature of some of the cryptographic assumptions. This is especially true in pairing-based cryptography that underline the security proofs. There's the cryptographic assumptions that are what the reduction argument in the security proof is based on a certain assumption about hardness of a certain type of problem. And a lot of these cryptographic assumptions, these hardness assumptions about certain problems, are quite exotic and look to most readers anyway as very unnatural. Now, there in the Pairings 2008 conference was a statement by Xavier Boyan giving a very positive spin to all these cryptographic assumptions. He said, "The newcomer to this particular branch of cryptography will be astonished by the sheer number and sometimes creativity of these assumptions. In comparison to the admittedly quite simpler algebraic structures of 20th century public key cryptography, the new bilinear groups offer a much richer palette of cryptographically useful trapdoors than their unidimensional counterparts." So, on the one hand, we see the trend of rather bold and boastful writing by crypto researchers. And again, I include myself, at least at some of the titles of my talk in 2000 and my paper with Mike Fellows in the 90s, that I've been guilty of this at times. And on the other hand, we see a long history of misjudgments and uncertainty and mistakes that continues to the present day. So this raises the question, how can we reconcile the disciplinary culture of our field with the reality of the history of our field? And I was thinking about this and wondering, is there any sort of key to resolve this dilemma? And I was thinking, I'm going to be going to India for IndoCrypt in December. And so it occurred to me, well, maybe I can look and see if the wisdom of ancient India has anything to tell us about this. So sure enough, I looked in the Bhagavad Gita, and in chapter 13, there's a section where the all-knowing one, Krishna, describes the quality that are necessary for knowledge. So this is something that anybody interested in knowledge should be aware of. And the very first one is amanitvam, which, if any of you know Sanskrit, please excuse my mispronunciation. But so amanitvam is the most important quality. The English translation is humility. So it occurred to me, here's Krishna, but I didn't show pictures of various people, but I did show Krishna. So if we make a thought experiment and imagine that Krishna were brought in as a consultant. Now, and this isn't very realistic. I'm sure Krishna would not agree to sign a non-disclosure agreement. But let's just, as a thought experiment, suppose that Krishna were brought in as a consultant on how to improve research in cryptography. And he went to work reading through some of the introductions and abstracts of articles on the ISAR ePrint server. And he read the Pairings 2008 paper by Boyan and the preface to Katz and Lindell. I think it's fair to say that most certainly one of his central recommendations to us for what the cryptographic community badly needs is a healthy dose of amanitvam. Okay, thank you.
Any questions for Neil?
Okay, I agree with what you say about Williams, because making more and more assumptions of various types, it has to be looked at in scrutiny rather than with. However, the idea about God's and little people, if you have a reduction, okay, to something simpler, simple stage. I mean, it's better to have a reduction to something that could be stated in one line than to assume that the algorithm works. Don't you agree? That's all they seem to say. Well, how could that be considered?
No. What you're saying makes good sense. That it's better to have it than not to have it. But I think what they're saying is more than that. They're saying that these so-called proofs of security, and I don't really object to the proofs of security so much as to their name. If they were called something else, like a reductionist argument that gives a certain amount of evidence, that would be fine.
It's a reduction, so
it gives some sort of evidence for something. But to say that it transforms our field into a science is, I think, going too far. So I'm not objecting to the idea of giving a reduction as a form of evidence that there's a close tie between a certain protocol and a certain mathematical problem that's conjectured to be difficult.
why do you say there's a close tie? The statement is very rigorous. The statement is that if there's an algorithm that breaks the crypto system, okay, then there's an algorithm to solve the computational problem that's been shown equivalent. So the government, either your crypto system is good, or you can say, either, you see what I'm saying?
Sure. First of all, assuming that the proof is correct and not fallacious. And second of all, there can be other issues that come up, such as a lack of tightness in the reduction. There can, of course, be many attacks on the protocol that might not be in the model. So I agree that is saying something precise, assuming that the proof is not fallacious. But to interpret it, I think, is a serious issue. And I don't think that it's reasonable to go around telling the general public that you have a proof of security and you've transformed. I don't mean you. I mean that we as a cryptographic research community have transformed cryptography into a science, and that we should call it a proof of security.
Certainly, you can't call it proof of security. You can say it should show that it's as secure as something else. But about fallacious proofs, I mean, they occur in mathematics not only.
Sure. Yeah. Thank you, John.
Yeah, I mean, it reminds me of a discussion that I was having earlier about what is sort of a mathematical conjecture rather than a hope-for statement or an utterance. I mean, there's lots of things that one can state. I mean, so I think sociologically, maybe mathematicians tend to be, for the most part, a little more conservative, on actually announcing something as a conjecture rather than saying, gee, wouldn't it be nice if the following is true? I mean, that seems to have a different status than saying, I conjecture this. Usually, if you say, I conjecture this, you usually associate it with some other thing. At least you give a plausible argument, why it seems to fit in with other, believed things or other theorems, rather than just saying, wouldn't it be nice if this were true?
And mathematicians are even more conservative yet about saying that this is a proof. Yeah, Rich.
I think you've been a little too hard on the automatic theorem proving people. We have a relatively limited number of theorems, perhaps 100 or something. And it's not inconceivable that we could insist that the people who write the papers force their supposed theorems through a checker without having to have the force through generated in some automatic sense. It's just the checker part that has to work.
It would be interesting to know if anybody can come up with an automatic way that would have, in retrospect, would have found the fallacies in the most scandalous cases of fallacious proofs. And I should say that some of these fallacious proofs were done by very prominent, very good people. It's not something that was done casually. Some of them were quite. One in particular that I'm thinking of was an extremely subtle fallacy in the proof that took cryptographers 7 years to discover that it was there. And a real test, I think, for automatic for this type of software would be to go back and put that original proof into it and see if it would find that fallacy. My understanding of the state of the art is that they're very, very far from being able to do anything like that. But maybe I'm wrong.
Well, they claim to force through a proof of the prime number theorem, for example, from basic axioms. So it's not inconceivable.
Okay. Thank you.
Anyone else? And I would ask you to join me in thanking Neil.